In the next few class, we shall consider the Lagrangian of few very special system. As for example, today we shall consider the Lagrangian of a charged particle when subjected to an electromagnetic field. So the electromagnetic field is characterized by the equation that curl of E is equal to minus del B del T, and we know that B, divergence of B is equal to 0, which readily suggests that B can be written in terms of the vector potential such that B is equal to curl A. And if we write this B over here, then we get curl of E is equal to minus del T of curl of A, or curl of E minus del A del T is 0, which suggests that E minus del A del T, sorry, this is E plus, which E plus del A del T can be written as minus grad phi, where A and phi are called the scalar potential. So we write E as minus grad phi minus del A del T, and we write B is equal to curl of A. Another thing that if you note that the gauge invariance of electromagnetic potential, the gauge invariance is that if we change phi to phi prime, where phi prime is phi minus del chi del T, where chi is any function of position and time, and at the same time we change A, vector potential A to A prime, so that A is equal to grad chi, then we find that E prime is equal to minus grad of phi prime minus del A prime del T, so that this is minus grad of phi minus del chi del T plus minus del T of A plus grad chi. So we get it that minus grad phi, then del A del T, then we have this term plus grad of del chi del T minus del T of grad chi. Since the order of partial differentiation is immaterial, this part is 0, so we get E prime is equal to E. So under this transformation of electric and magnetic field, the electric field remains same, and similarly B prime is equal to curl of A prime is equal to curl of A plus grad chi. Since the curl of divergence of any field is 0, so we see that under this transformation the field vectors E and B does not undergo any change. This is called the gauge invariance of the potential, and so we write the gauge invariance or gauge property that chi prime is equal to phi is equal to minus del phi del T, and grad phi gives us the same E, and B prime is equal to E and B prime is equal to B. So these are the concepts that we shall require in the subsequent development. With this tool, now I go to the force that acts on a charged particle, the force that acts on a charged particle charge is q. So it is E plus V cross P, the Lagrange force. In terms of the potential, this becomes Q. This is correct. Now, del t, we break it up in components. So this is now we recall that the vector potential is a function of position and time. So dA dt is equal to del A del t, the time dependence, explicit time dependence, plus del A del x dot, plus del A del y dot, plus del A del z dot. So this is del A del t plus this can be written as v dot grad on A, because v dot grad, this operator is x dot del x plus y dot del y plus z dot del z. So this, you see that there are these two terms which can be coupled to give us this. As dA dt del A del t plus v dot grad A. Now we couple these two terms. So we write q times minus grad of phi minus v dot A. So we have changed the potential in such a way. And there is this term. This term is left. Now the vector A can be written as a gradient operator with respect in velocity of space times V operating on A. So A operator, we first consider this operator. We consider a gradient operator in velocity space. This is I cap del Vx plus j cap del Vy plus k cap del Vz. If we define this, then V dot, if we consider this gradient operator operating on V dot A, so this is I cap del Vx j cap del Vy plus k cap del Vz. It operates on Vx Ax, Vy Ay, Vz Az. Now when this operates, since is the vector potential of the function of position and time. This operator does not operate on is. So we get, this is I cap ax plus j, when this operates only on this ay plus k cap az. So this is vector A, nothing but vector A. So we can write this part, the minus dt of A. The A part is written as v dot A. This is done in order to bring a similar term like this, as A is equal to, this is vector operator v dot A. This is a velocity dependent part. You recall that the scalar potential phi is a function of space coordinate and of time. So the scalar potential do not have any time dependence on velocity. Keeping this in mind, we can write this as what I have done, I have introduced this part which is 0, so 0 part is introduced, and we write it as where u, the function u, it is a function of position, velocity and time. It is equal to phi of rt, sorry, q is there, so then we write where u is a function of position, velocity and of time is equal to charge q times scalar potential phi, which is a function of position and time, minus v dot A, which is again a function of r and t. So this is known as generalized potential or the velocity dependent potential. This is called as generalized or velocity dependent potential. We have encountered such potential while dealing with non-conservative system. Indeed, these forces are non-conservative because neither for electrodynamics curl of E is equal to minus del V del P, which is not in general 0, and curl of B is equal to mu 0 J if we consider the Ampere's Archital law in its original form, and then you have mu 0 JD, the displacement current, if we account for Maxwell's correction. So again, this is not equal to 0. So the electromagnetic force is not at all a conservative force. So the non-conservative force, as we have talked earlier, can be accounted by a velocity dependent potential. This is a specific example where the potential is a velocity dependent potential. So our conclusion is that for a charged particle when subjected to electromagnetic field, it can be taken into care taken care of through the velocity dependent potential. So this is how this is equal to with u is equal to q phi minus v dot a. Now we come into the Lagrangian. The Lagrangian of a system is generally defined as A is equal to P minus P, where V is the potential which accounts for the conservative part of the field. When the potential is partly conservative and partly non-conservative, then the conservative part can be taken care of within L and the non-conservative part can be taken care of through the generalized force. Or we can introduce a modified Lagrangian L is equal to P minus U. So we shall adopt this. Recall that there are different methods for adopting the non-conservative force. Let me remind you that this can be written as del T of Qk dot minus del T del Qk is equal to Qk when force is completely non-conservative, or we can write it as del L del Qk dot minus del L del Qk is equal to Qk non-conservative. So the conservative part is taken care of through the V term, or we can deal this problem as by introducing the generalized Lagrangian this is 0. Here we are actually defining the generalized Lagrangian. Still we are using L, not the cursive L. This is the generalized Lagrangian. So the Lagrangian equation will be this. So let me first write the Lagrangian. So this is half mv square minus u means phi minus v dot a. This is equal to half m x dot square y dot square z dot square minus q phi x dot ax plus minus y dot ay minus z dot az. Now del L del x del L del x here is no x dependent, phi has the x dependent, so this is minus q times del phi del x, and all these terms ax, ay, az have the x dependencies. So this sign is plus q x dot del x y dot del ay del x plus z dot del az del x. This is del x, and del L del x dot is equal to half, mx dot from here, and from there we get plus qax Similarly, we can find the y and z components. If we write it in vector form, so this is px. So this px, this part is called the kinetic momentum. Kinetic momentum, and this part is called the field momentum. So this is the contribution to the momentum coming from the electromagnetic field, hence it is called field momentum, and it is the kinetic momentum, kinetic TIC. Now let me write the Lagrangian equation for it. The Lagrangian equation is ddt of del L del x dot is equal to del L del x. So ddt of this thing, first we have ddt of mx dot plus qax. On the right hand side we have del L del x is equal to minus q del phi del x plus q, then this term. Let me write it. Plus q x dot del x del x plus y dot del y del x plus z dot del z del x. Now this has two terms. First term is mx double dot. Now in non-relativistic mechanics there is no variation of mass, mx double dot. Then the next part is q d. This is mx double dot, the first term. Second term, q dax dt, and right hand side you have all these terms. X dot you now recall that dax dt is equal to del ax del t plus x dot del ax del x y dot del ax del y plus z dot del ax del z. So we write the left hand side as mx double dot plus q del ax del t plus x dot del ax del x plus y dot del ax del y plus z dot del ax del z. On the right hand side we have minus q del phi del x plus this term q times phi dot del ax del x plus y dot del y del x plus z dot del z del x. Here what we have done, we have replaced this total derivative in terms of the partial derivative. Note carefully that this term is cancelled because it is on the both sides. So we rewrite the equation as mx double dot is equal to q is all in all the terms, so we take q common. First term is minus del phi del x, and this term is minus del x del t. So this is a term. Then we take the y dot term first. Y dot term is del a y del x minus del a x del y, and then z dot term is del a z del x, this term, and this term is with a negative sign. Recall that B is equal to curl of A. This is equal to I J K del L X del L Y del L Z A X A Y A Z. So B by is del ax del z minus del az del x, and bz is equal to del ay del x minus del ax del y. So this term is nothing but bz. This is bz, and this term is with a negative sign minus by. So we write it as minus q times del phi del x minus del x del t plus this is by bz minus bz by. So this can be written as q times, sorry, there is no minus q times and this is b cross b's x component. So in vector form we can write the equation as, so in a vector form the equation is q times, this is grad phi minus d vector a dt, and this is v cross b, which is, this is nothing but e. So this is equal to q times e plus v cross b. So what we have done? We started from the Lagrange force equation, this, and used electromagnetic potentials to finally get the generalized potential function u, from where we have developed the generalized Lagrangian, which is for a velocity dependent potential. Then we go to the Lagrange's equation corresponding to the generalized potential, and with certain mathematical vocabulary we have ultimately arrived at the Lagrange force equation. So we have established is that the consideration of electromagnetic field, or the behavior of charged particle within an electromagnetic field can adequately be taken into consideration through this generalized potential. One more thing, we have defined the momentum vector like this. So the vector momentum is this, which is mv plus qa. If we write kinetic energy T, this is half mv square, which can be written as P minus qa square by 2m. So that we may say that the momentum when a particle is subjected to electromagnetic field, the momentum P is changed to P minus qa. Similarly, when we consider the Hamiltonian dynamics, we will see that energy E shifts to E minus q phi. Another thing that what will be the effect of gauge transformation on the Lagrangian. So this is another point of interest that should be addressed. So we define the Lagrangian in terms of potential phi and A in this form, and we modify the Lagrangian using the gauge property, and we redefine the Lagrangian as L prime. Lagrangian L prime is equal to half mv square minus q pi prime minus v dot a prime, and we use this property for v prime and half mv square minus q. This phi prime is phi minus del chi del d. This is the change of scalar potential minus v dot. A is changed to A plus grad chi. We write it as half mv square minus q times phi minus v dot A. Then there are this q taken common minus q taken common. Then we have del chi del d. Okay, this is v dot grad chi. Sorry, there is a sign mistake. When we have made it, this sign should be plus, so this is plus. So this part is nothing but d chi dt, and where we have already mentioned that chi is a function of rt, so we can consider it to be a gauge function. So this part is L plus q times d chi dt. So this can be treated as the gauge function. So Euler-Lagrange equation also remains invariant under such gauge transformation. This is all about the Lagrangian dynamics of of a charged particle when subjected to an electromagnetic field. After introducing ourselves with the Hamiltonian dynamics, we shall do a little bit of the Hamiltonian dynamics of a charged particle. That's all for today. In the next class, we shall consider the Lagrangian of a relativistic particle.